So, continuing our discussion of extragalactic astronomy beyond the Milky Way, we ended talking about how we have this distance pyramid in which we are able to measure the solar system. The solar system allows us to figure the next step, parallax of stars, which allows us to figure out how to do main sequence fitting, because then we learn the HR diagram, and that allows us to measure distances nearby in the galaxy beyond where parallax would measure. And then we could then discover Cepheid variables and how they work, and that allows us to measure the distances to nearby galaxies using the period luminosity relationship. That allows us to figure out about the Tully-Fisher relationship. That allows us to figure out distances even farther away, which allows us to figure out white dwarfs are all the same when they explode. Type 1A supernovae are all about the same brightness. And so again, everything from parallax onward is based on what we call standard candles. 10 raised to the m minus m plus 5 or 5 magnitudes. And so we got to figure out the absolute magnitude. But doing all that, using all the different ways of measuring at different distances, that allows us to plot this relationship in which we have the distance on the x-axis, the velocity on the y-axis, and they have a trend. The slope of that line, remember, slope is rise over run, so it'll be velocity divided, change in velocity divided by change in distance. That slope is the Hubble relationship. So velocity equals hd. And again, we really ought to call it Hubble-Lemaitre constant. About 70 to 75, modern estimates about 73 kilometers per second per megaparsec. Now we're going to talk more about this to come later on, next week maybe, or right near the end of the semester. But for right now, we've got a little more work to do just about galaxies themselves. Our galaxy, the Milky Way, is part of a clump of galaxies that we call the local group. And as we look out across the universe, we see very few galaxies out there that are just isolated galaxies all by themselves in the universe. Almost all galaxies are part of groups of galaxies or clusters of galaxies. So that's our next topic of study, is galaxy clusters. Some galaxy clusters are very compact, that have a lot of galaxies and all over the place, and that we call those rich clusters. Some galaxy clusters are pretty big sized things with lots of galaxies in them, but they're all pretty far apart. Those are sparse clusters. And a few of them are just a handful of galaxies that are clumped up near each other, and we call that a group. Our Milky Way galaxy and the Andromeda galaxy are the two big galaxies that make our little cluster. And there's a medium-sized galaxy, M33, and then a whole bunch of small galaxies, and so little dwarf things. And so our little cluster that we're part of is a group, the local group. Milky Way is kind of at one end of it. The Andromeda galaxy is at the other end of it. So you get the Milky Way, got the Andromeda galaxy, M33, there's a handful of galaxies around there, satellite galaxies here, a few other little dwarf galaxies moving around, and so forth. And so that's the local group. Interestingly enough, our local group has a galaxy, one of these rare lone galaxies that's moving away from it, Dwingaloo 1. Discovered by the Dwingaloo radio telescope in the Netherlands. And so what we think happened was that it used to be part of our local group. So we had the Dwingaloo galaxy, we had M31, M33, and we had the Milky Way, and all these things were moving around each other. And what happened was the Dwingaloo 1 galaxy and M31 got really close together, and when they did, Dwingaloo 1 slung out faster and got thrown out away from the local group, and M31 went spiraling off this way, going too slow, in fact. So actually it's actually falling towards the Milky Way right now. And so that's why it's one of the very few galaxies out there, about the only one, in fact, that's blue shifted heading towards us. So some textbooks list Dwingaloo 1 as a lone galaxy. Some textbooks list it as a very far off member of the local group, and some of them list it as an ejected member of the local group. It's very difficult to see because it's right behind the Milky Way, and so this picture here is in infrared taken through the Milky Way, looking at it. Now, obviously, it's a big, nice, large spiral galaxy. Galaxies have an interesting property. They tend to run into each other. Stars are very, very far apart, so stars almost never run into each other. But our next topic of study is going to be galactic interactions and how they do interact with each other.